Lesson 4, collisions in 2 dimensions. So these are collisions that do not happen in a straight line. So for example, if we had a car traveling north and it crashed into a car traveling east, that would be a 2-dimensional collision. When we're working with 2-dimensional collisions, we have to follow some rules. So we actually have to break the momentum vectors into components, and we're going to find the total momentum in the x direction, and that's going to be conserved. So that means the total is going to be the same before and after. And we're also going to find the total momentum in the y direction, which will be conserved as well. So to explain how to do this, we're going to look at this example here. We have 2 objects, A and B, and everything that's happening within this box that I'm drawing, that is before the objects collide. So for object A, we know its mass, we know its speed, we know which angle it's moving at. For object B, we know some information as well. And in this particular case, they're telling us in the question that when objects A and B collide, they're going to stick together, and we want to find the velocity of A and B together after the collision. So since this is a 2-dimensional collision, we're going to break things into components. To help us keep track of our numbers, it's a good idea to draw a chart like the one that you see here. This chart will not be drawn for you on quizzes or tests, so make sure you know how to draw it for yourself. So what we're going to do is we're going to start by calculating the momentum of object A before the collision. So the momentum of object A is going to be A's mass times A's velocity. So that's going to be 3 kilograms times 2 meters per second, which is going to be 6 kilogram meters per second. So 6 kilogram meters per second is represented by the black arrow that's already drawn there for you. Now, 6 kilogram meters per second, that's the momentum of A. It's not an x component or a y component. It's just A's overall momentum. So what we need to do is we need to break the overall momentum into components. Remember to draw those components as arrows. So since the overall momentum points sort of southeast, my y component is going south and my x component is going east. And actually I'm going to call those px and py because they're momentums. And we're going to go ahead and calculate those using trig. So for px, we're going to use cos of 30 times the overall momentum. And then for py, we're going to use sine of 30 times the overall momentum. And when we go ahead and put those in our calculator, for x, we get about 5.19 kilogram meters per second to the east. And for y, we get 3 kilogram meters per second. And we can see from the diagram that that one's to the south. Now, we're going to put those numbers into the chart just to help us keep track of them. So I'm just going to copy them down again. When I put them in the chart, I am going to put them positive for east or north and negative for south or west. So since I had 3 south, I'll write that as -3. So that's the initial momentum of object A. Now we're going to repeat all of that for object B. So for B's overall momentum, which again is represented by the black arrow, we're going to calculate mass times velocity. Okay, so the mass is 4 kilograms and the velocity is 5 meters per second. So the length of that arrow is 20 kilogram meters per second. And then we're going to go ahead and draw in our components. So we have our y component going north, and we have our x component going east. And let's calculate those. So x is going to be cos of 20 degrees times 20 kilogram meters per second. And y is going to be sine of 20 degrees times 20 kilogram meters per second. And putting those in my calculator for x, I get about 18.7 kilogram meters per second east. And for y, I get 6.84 kilogram meters per second north. So now that I've calculated those, I'm going to go back to the previous slide and I'm going to put these numbers for x and y into the chart. So for b in the x direction, that was about 18.7, and it's positive because it's east. And for y, it was 6.84, and that's positive because it was north. Okay, so now, because we care about total momentum, so when we're talking about conservation of momentum, it's never the momentum of an individual object, it's always the total momentum for the whole system, or in other words, it's the total for both objects together. So what we need to do is we need to go ahead and add our two x components together to find the total in the x direction. And when we do that, we should be getting 23.99. And then we're also going to add our two y components together. Don't forget the negative in front of the 3. And that's going to give us 3.84. So that is our before table filled in. Now, the next thing we're going to do is we're going to actually create another table for after the collision. Remember that what conservation of momentum says is that the totals have to be the same. So you're going to have two different tables. In both tables, the row that contains the totals is identical. So I'm just going to take the totals that I had from my before table and I'm going to copy them down here in the after table, exactly the same numbers as before. Now you'll notice that in this table, I only have one row above the total row. And that row is for A and B together. Remember, that's because this was a hit and stick collision. So I'm treating A and B like they're just one object. So A and B don't get separate rows anymore. They just get one row in total. And whatever is above the totals, the rows above the totals have to add to the totals. But here there is only one row above the totals. So in this case, the row that I'm filling in matches the totals. Okay, so let's see how to use this to answer the question. So I'm just going to move this up so that it's not in my way. What we're going to do is we're going to find the momentum of A and B together after the collision, and we need to make a vector diagram to do that. So I'm going to draw a set of axes, and I'll go ahead and label it northeast, south, and west. And then I'm going to draw in my vectors. So you could either draw the x component first or the y component first. It doesn't really matter. I am going to draw the x component first. So here I'm drawing an arrow pointing east. I'm going to label it 23.99. And then I'm going to draw an arrow going north, and I'm going to label that one 3.84. And then I'm going to draw in my resultant. Okay, for the resultant, I am going to label this PAB prime. So this represents the momentum of object A and B together after the collision. And I'll just draw in the angle that I'm going to find as well. So for PAB prime, for that, I'm just going to do A squared plus B squared equals C squared. So 23.99 kilogram meters per second squared plus 3.84 kilogram meters per second squared, all under a square root. When you calculate that, you should be getting 24.2 approximately kilogram meters per second. And then for the angle, maybe just calculate the angle in a different color over here. So for the angle, we're going to do tan inverse of the opposite side over the adjacent side. So of 3.84 kilogram meters per second over 23.99 kilogram meters per second. And for that, I got about 9.1 degrees. And my triangle, my angle is touching the east axis right here. So north of east, remember east has to be written last. Okay, now remembering back to what the question was asking, it was asking for the velocity of A and B after the collision. So to find the velocity, we're going to have to take our momentum. So remember, the momentum of object AB is going to be the mass of A plus the mass of B times the speed of A and B together after. So I'll write a prime symbol. And actually, it's the velocity, not the speed. I said speed by accident. So rearranging the velocity of A and B together is going to be the momentum of A and B over MA plus MB. And actually, let's make sure we've drawn our prime symbols everywhere that we're supposed to. So just have a look at where I've put them. And then now I can plug in my numbers. Okay, and the mass of object A was 3 kilograms, and the mass of object B was 4 kilograms. When you calculate that, you should be getting about 3.5 meters per second. So for my final answer, everything is to 2 significant digits. So 3.5 meters per second, 9.1 degrees, north of east, and done. When you are filling in the charts, so the table for before the collision and the table for after the collision, make sure that you use momentum, not velocity. So it's not true that velocity is conserved. So if you were to fill in the charts with velocities, that would give you a wrong answer. So that's why my first step is always to calculate the momentum of the objects, and then I go from there.